2.7. In this video, I'll be covering the detection of DNA and RNA using spectroscopy, and it's the last section for the nucleic acids topic. With that in mind, what is spectroscopy? Right? It's us as scientists probing chemicals with light. So if we have some sort of chemical sample, we can shoot different types of light through it, and seeing how that light is absorbed or displaced by the chemical gives us information as to what the chemical is. So we're going to use this kind of technique for analyzing DNA and RNA, and specifically of note, the nucleic bases are capable of absorbing UV radiation. So ultraviolet radiation, which if you recall from earlier science is quite high energy, right? Typically we view the red to the orange. This is our visible light spectrum of 700 nanometers of light to 400 nanometers. Ultraviolet is lower in wavelength, but higher in energy than purple. So it's ultraviolet. This energy range is where these DNA bases, G, C, A, and T, actually absorb. And that kind of makes sense if you think about UV rays from the sun, or UV rays rather from the sun. The ultraviolet rays are the ones that are dangerous, right? Because they can actually be absorbed by DNA bases. So that makes a lot of sense, right? Sunburn damage is damage to DNA, right? Damage from the UV to DNA. So wear sunscreen. Anyway, let's understand how spectroscopy works and how we can use it to probe DNA and RNA by first looking at absorbance plots. So to understand this, we have to first talk about absorbance, and that's on the y-axis here. Basically, we're going to shine a light through the chemical, and if the light is absorbed, that means that the chemical is absorbing the light. We see this line go up, close to 100% absorbance. Right? For double-stranded DNA, this is the blue line, we see that the x-axis is wavelength. Right? So the wavelength says here we have high energy, here we have lower energy, but this is in the ultraviolet range, again 230 to 300. And we can see that there's a peak. So different wavelengths absorb differently by double-stranded DNA. And we can see that around 260 here is a peak. And that peak tells us that this is the highest amount of absorbance that we're going to see from double-stranded DNA. It likes to absorb that energy. What's interesting is that single-stranded DNA has a similar trend. Right? It's just a little bit higher in absorbance. And these are approximate lines, by the way. But protein is very interesting, right? So for single-stranded DNA, I should just wrap up that it's a little bit better at absorbing, but it still has a peak absorbance at 260 nanometers. That's its favorite energy. Protein's very different in that it's going to have a energy maximum, so to speak, around 280. So I colored that orange. Let me just change that here. Protein. And you can see that around 280, there's a peak of absorbance. There's a lot here as well, but we're ignoring that. So protein has a very different absorbance, right? It doesn't like to absorb at 260. It absorbs 280. So DNA, single-stranded or double-stranded, versus protein, they absorb at different energy levels and different energy kind of strengths. And that's what we're going to take advantage of, right? Real quick, before we dig into that further, let's take a look at measuring absorbance. So the idea here, when we talk about absorbance, is that we're shooting some sort of flashlight through a sample, and we're measuring what comes out the other end. Here, we had no sample, so there's just water, and we'll assume that 100% of the light was transmitted, which means 0% absorbance. On the other side, right now we have a bunch of DNA, double-stranded DNA helices in our sample. So if I shine, again back here, different energies, if I shine 260 nanometer radiation, right, so the energy of this wave is 260, that means that lots of that energy is going to be absorbed. Let's say that it's 80%, just throwing a number out there. That means that if I put 100 units of energy, I'd only see 20 coming out the other side, right? That means that there was an 80% absorbance. And so we have very fancy machines that can measure the light passing through a sample and give us an idea of how much light is going through. And from that, we can actually figure out a concentration of DNA. Now, the math behind this is the Beer-Lambert law. I'm not going to go into too much detail on this topic, but the basic idea is that this is the absorbance measured, This is a constant value called the extinction coefficient. So it depends on what the sample is. This is the length of the tube. So you can imagine a very thin tube and a very thick tube. Light can go through this easier than it can go through this. So the length of the tube has to be factored in. And last but not least, the concentration. So of the thing that is the constant, right? So DNA has a specific extinction coefficient on average. And if you can measure the absorbance and you know that you're measuring for DNA and you know the length of the tube, you're able to then solve for concentration. And that can be really useful to know the concentration of DNA in something. But that's the first technique, right? We're using absorbance via this law. I'm not going to go into this much deeper. It's not commonly tested, at least at the University of Alberta, but I did want to bring it up here. Now, one of the main uses is assessing for purity. So if we're assessing for purity, that can be a different, another use of this technology. So here we again have absorbance. Recall that DNA has a peak at 260 and protein has a peak at 280. So that distinct difference, right? If we have a sample that has DNA and we just want pure DNA, but it's contaminated with protein, the light's going to be absorbing at 280 when we don't want it to. A pure sample of DNA should only have this blue line. It's only going to be absorbing well at 260 and around, but it shouldn't be absorbing that good at 280. Where protein is going to have very low absorption. But this is hard to disentangle. So what we're going to do is use the absorbance 260 to 280 ratio. So we take the total absorbance of 260 and of 280, and we divide them by each other. And this isn't something you're going to need to really do much math on or appreciate, but a basic idea is that if you have pure DNA, you're going to be dealing with around 1.8 to 2 as your unit. Right? If you're contaminated with protein, we can think about what would happen, right? More protein means that A280 is going to be big. A260 will be small. So this number actually gets smaller to around 1.4. Or anything lower than 1.8 tells you your DNA is not that pure. Again, that's the ratio of 260 to 280. So in case one, if we think about understanding this ratio, if we have pure DNA, the absorbance at 260 should be high because DNA absorbs well at 260, but low at 280. This gives you a high ratio of around 1.8 to 2, which tells you you have pure DNA. If you have pure protein, you're going to see a very high amount of A280 and a low amount of A260. That gives you a lower value, which tells you that it's impure. And again, same with contaminated DNA, right? You're going to have a high A260 because there's DNA present, but you'll also have a high 280 because there's protein present. And again, you'll see a value, maybe 1.6, for example, right? Again, taking the 260 over the 280, that tells you that you have DNA there, probably, but it's impure. There's other things like protein that are contaminating your DNA. So again, using absorbance of these different wavelengths as a way to kind of not just get the concentration of your DNA, but also get an idea of its purity. Now, one last use for UV spectroscopy is tracking the secondary structure of DNA, as we covered last time. Here we have 2 individual strands of DNA, and here we have the double helix. If the 2 strands are combining together, we call this annealing. And if they're breaking apart, we call it denaturing or melting. Right? When they melt apart and come in their own separate 2 strands, they can combine or anneal, or they can melt. And so this can be very important. PCR is something that is very built on this technique, and I'm not going to cover it in this class, in this course, but I highly advise you to watch some really excellent YouTube videos by Veritasium on PCR. He has some very excellent content that covers how PCR works, but it's based on annealing and melting DNA, and we use it all the time for basically everything. So what does that look like? Remember that single-stranded DNA provides a slightly higher signal. It still absorbs at 280, but there's a higher signal. Right? The idea is that when we go back to this concept of melting and annealing, that at high temperatures, we can actually melt the 2 DNA sequences, right? They want to base pair, but at high enough temperatures, they're just going to be separate. And at low temperatures, they will combine together with their complementary sequences, right? Two different pieces of DNA that are complementary to each other. But when they anneal, so if they're at low temperatures, right, the double-stranded DNA at low temperatures, that's going to be there, but the high temperatures is single-stranded DNA, and you'll be able to measure that difference in signal as a change in your absorbance. So before we dig into what that curve looks like, keep in mind that the core idea is single-stranded DNA gives you higher values. And so we can measure if a double-stranded piece of DNA turns into a single-stranded pair, we'll actually measure a decrease in signal. So what does that mean? Right? Or rather an increase in signal. Here we have double-stranded DNA, here we have single-stranded DNA, and here's temperature. Right? What we can see is that as we increase the temperature, it remains double-stranded until a certain point. There's a certain critical range of temperatures where suddenly the signal, the amount of absorbance that says, hey, we have single-stranded DNA, that goes up. We call this period, this area, the melting zone. I call it the melting zone, but you can call it whatever you want. The thing that you can't give a justification for is if you right in the middle of this line, right, where the sample is kind of halfway in between the top and bottom at 50%, we can draw a line down, and we call this Tm, the melting temperature. So this isn't the temperature where the melting of the DNA starts. It's the exact middle zone. It is when 50% of the DNA is melted, is split into single strands, right? So the Tm of a DNA sequence will give you an idea, right, the melting temperature, of how stable that DNA is. And this comes back to something that's quite interesting, which is how can you predict, right? Are some DNA pairs, the secondary sequences, these, the helices, are they more stable than others? Well, there actually are differences, right? Some and different pieces of DNA will have different TMs. So again, we're measuring the intensity, right? So double-stranded DNA, the helix, when it's applied to high temperature, it'll melt and give a higher sequence, or rather a higher absorbance value. And we detect that change in absorbance value with that DNA to say, hey, well, at what temperature is it actually melting? Because we can see when it's fully melted, we know when it's fully annealed, this is the midpoint. So keeping in mind that a low TM, or rather a high TM, I should say, means that you are a very stable piece of DNA, right? Because you, even at high temperatures, are able to stay together, where a low TM means that you're very quick to break into pieces. So factors that can influence the melting temperature, there are a couple, right? Based on the DNA sequence, think about G and C content. So remember that guanine and cytosine have 3 hydrogen bonds, where adenine and thymine have 2 hydrogen bonds. The more G and C content you have, right, these are more sticky. So the more of them you have, the higher the melting temperature, the more stable those interactions are. So if you have more GC content compared to A's and T's, right, by Chargaff's rule, then your DNA sequence is going to have a higher TM. Another thing to consider as well is the length, right? Longer sequences will have more interactions than shorter ones, and they should be generally stickier. That's not saying that length is longer is always going to be higher TM, but generally that's one of the factors, right? Environmentally, there's a lot of other things, right? So for example, exposure to acids or salts, right? In water and in the cell, DNA is very happy to stay together. But if we expose it to things like high salt concentrations or low salt concentrations, if we expose it to acids or bases, these are conditions that will absolutely change the melting temperature and perhaps make it no longer feasible for these things to stick together, right? So some things are based on the intrinsic, the TM of the DNA sequence because of the base pairing, and others are, in the environment. Of course, in biochemistry, a core concept is that the environment isn't changing that much. We're not in a test tube where we can add acids and bases. We're in the nucleus of a cell. Just to understand the impact of GC content, right, as one of those things that affects the melting temperature, again, we're measuring the relative A260. So Up here, we're looking at individual strands of DNA at high temperature. Down here, we're looking at a helix. And here, it's 50-50 at the TM. Right? If we assume that this DNA sequence helix here is 50% AT and 50% GC, what would it look like if we had 25% GC and 75% AT? So a lot less of the Gs. Well, that means that there would be less triple hydrogen bonding and more doubles. Overall, there's less hydrogen bonding. So we would expect the curve to look like this, where it would start melting at a lower temperature. With 75% GC content, the opposite is true, right? More GC means more hydrogen bonds, means that we'll be able to get to a higher temperature. So the TM of high GC is going to be a bigger number because you need to get to a higher temperature to melt it, where the TM here is lower. Right? That's how we can understand with these graphs the melting of different DNA. Now, this is going to be useful for advanced biochemistry, for different, laboratory techniques. But for now, just understanding the impact of GC content on melting temperature is plenty. With that, we've covered the different structures and functions of DNA and RNA and the tools to measure them. So let's move on to what I find more interesting, the protein structures. I'll see you in section 3 to discuss protein.